In this video, you will learn about strong acids and bases. You will need to do some memorizing to make this topic understandable. You will also learn about the differences between weak and strong substances. The first and last parts of this video will be about pH values, where you will be expected to calculate this quantity. An acid is a proton donor, and a base is a proton acceptor, or a hydroxide ion donor. A proton is a hydrogen ion, or H+, and can also be represented as H3O+. I will use these notations for a proton interchangeably throughout these acid-base videos. A hydroxide ion is represented as OH-. Concentrations of H+ or OH- are usually very small, and pH is a way of making small concentrations into workable numbers. The pH is the negative log of H+ concentration, or the negative log of H3O+ concentration. In fact, when you take the P of anything, you take the negative log of that number. pOH is the negative log of the concentration of OH-. pK is the negative log of the equilibrium constant K. Pause the video now to find your calculator and to locate the log key. To calculate the pH value, take the log of the number first, and then reverse the sign. To calculate pH values, we will start with strong acids and strong bases. There are 6 strong acids that you should memorize. They are HCl, HBr, HI, HNO3, HClO4, and H2SO4. If you see another acid and it is not one of these, it is weak. What do I mean when I say weak and strong? Strong acids, when placed in water, will completely dissociate, which means they will exist as their ions. There will no longer be any of the acid left in the solution. Compare a strong acid, such as HCl, to a soluble salt, such as NaCl. Both, when dissolved in water, completely exist as ions. There is no HCl or NaCl left in the solution when the concentrations are low. HCl aqueous plus H2O liquid reacts to form Cl- aqueous plus H3O+ aqueous. This is a single arrow because it will completely form the products. There will be no reactants left. A weak substance does not completely dissociate in water. There will be some ions and some acid or base left in the solution. In this case, there is an equilibrium between the acid and water and the ions. A generic weak acid, Ha aqueous plus H2O liquid, is in equilibrium with A- aqueous plus H3O positive aqueous. This is represented by an equilibrium arrow because some of the products will become reactants and some of the reactants will become products at equilibrium. There are 7 strong bases that you should memorize. They are LiOH, NaOH, KOH, RbOH, CSOH, SrOH2, and BaOH2. These are all the group 1A metal ion hydroxides, barium hydroxide, and strontium hydroxide. The ones that are underlined are bases that can lose 2 hydroxide ions per every 1 base molecule that dissociates. Also, the underlined bases can only dissociate into solutions of 0.01 molar or less. The other bases can make solutions of 1.0 molar and are 100% dissociated into that concentration. To calculate the pH of an acid or a base, first write a reaction equation. For example, if we have a solution of RbOH aqueous, it will dissociate to form Rb+ aqueous and OH- aqueous. Since there will be no equilibrium reaction, the initial concentration of the RbOH will be the concentration of the OH-. Then you can calculate the pOH of the base by taking the negative log of the OH- concentration. This also works with strong acids. The initial concentration of the acid equals the initial concentration of the H3O+. Once you have the pOH, how do you find the pH of the solution? You do this by using the auto-ionization of water equation. Since water is both an acid and a base, 2 water molecules can auto-ionize automatically, to form H3O+ aqueous and OH- aqueous. This is an equilibrium reaction that has very little K value, which means it is highly reactant favored. This K value is given a special symbol, Kw, because of water. This Kw value equals the concentration of H3O plus times the concentration of OH negative and has a value of 1.0 times 10 to the negative 14. The reason the H2O is not in the Kw expression is because it is a liquid, and liquids are not included in equilibrium expressions. So, if you know your H3O plus or OH negative concentration and are looking for the other, you can substitute 1 into this equation. The concentration of H3O plus times the concentration of OH negative equals 1.0 times 10 to the negative 14 to solve for the other one. An easier way to do this is just to take the negative log of the entire equation. Then we have negative log of H3O plus concentration times the negative log of the OH negative concentration equals the negative log of 1.00 times 10 to the negative 14. The negative log of the H3O plus concentration is also the pH according to our previous discussion. The negative log of OH negative concentration is the pOH, and the negative log of 1.00 times 10 to the negative 14 is 14.00. If you plug in these things to our previous equation and utilize the rules of logs, you come up with pH plus pOH equals 14.00. There are some really attractive features about pH values, including specific rules for significant figures for pH values. Now, I know I hear you all groaning, sig fig rules again, but hear me out. They will make your life easier. The 14 from the previous slide is not considered when determining the number of significant figures in a pH value. This is because any pH value is the negative log of the H plus concentration. So the number before the decimal place defines the exponent in the concentration term. The only number that is significant in the pH value is behind the decimal place. So, for the 14.00 from above, the 00 is the significant part. Usually, pH values are calculated to 2 decimal places because this is the precision of pH meters. Since the pH is a logarithmic scale and concentrations usually have exponents, the number before the decimal in a pH is normally the exponent in the concentration value. A 1 unit change in pH value corresponds to a 10-fold difference in hydrogen ion concentration. Also, since we are taking numbers to their logs, pHs and pOHs are unitless. pH, along with being a more convenient way to represent H3O plus concentration, is also a measure of the acidity of a substance. A pH below 7 represents an acidic solution. The lower the pH, the more acidic the solution becomes. A pH above 7 represents a basic solution. The higher the pH, the more basic the solution becomes. A pH of 7 is a neutral solution. View this figure for a pictorial representation of pH. pH values and H3O plus concentrations are inversely related because the pH equals the negative log of H3O plus concentration. So, a large H3O plus concentration and a small pH represents a highly acidic solution and a slightly basic solution. A small H3O plus concentration and a large pH represents a slightly acidic solution and a highly basic solution. The pOH is exactly the opposite. A pOH above 7 represents an acidic solution. The higher the pOH, the more acidic the solution becomes. A pOH below 7 represents a basic solution. The lower the pOH, the more basic the solution becomes. A pOH of 7 is still a neutral solution. pOH values and OH negative concentrations are also inversely related because the pOH equals the negative log of OH negative concentration. A large OH negative concentration, small pOH, and large pH represents a highly basic solution and a slightly acidic solution. And a small OH negative concentration, large pOH, and small pH represents a slightly basic solution and a highly acidic solution. Now let's work on some problems using the concepts discussed in this video. 1. calculate the pH and the pOH of the following solutions at 25 degrees Celsius. Indicate if they are neutral, acidic, or basic. A. 1.35 times 10 to the negative 4 molar H3O plus aqueous. B. 4.58 times 10 to the negative 5 molar OH negative aqueous. C. 0.140 molar solution of HI aqueous. D. 1.25 times 10 to the negative 3 molar solution of SrOH2 aqueous. E. 0.340 grams of LiOH, molar mass equals 23.9 grams per mole, in enough water to make 500.0 milliliters of solution. For part A, they give us a 1.35 times 10 to the negative 4 molar H3O positive solution. To calculate the pH, take the negative log of the H3O plus concentration. Take the negative log of 1.35 times 10 to the negative 4, and you get 3.87. To calculate the negative log of a number, take the log of the number first, and then take the negative of the result. To calculate the pOH, plug the pH into the equation pH plus pOH equals 14.00. Then subtract the pH, and you have the equation of pOH equals 14.00 minus pH. And you find pOH equals 14.00 minus 3.87, which equals 10.13. The pH of solution is less than 7, therefore the solution is acidic. For part B, they give us a 4.58 times 10 to the negative 5 molar solution of OH negative. To find the pOH, take the negative log of the OH negative concentration. Take the negative log of 4.58 times 10 to the negative 5, and you get 4.34. To calculate the pH, plug the pOH into the equation pH plus pOH equals 14.00. Then subtract the pOH, and you have the equation pH equals 14.00 minus pOH. pH equals 14.00 minus 4.34, which equals 9.66. The pH of the solution is greater than 7. Therefore, the solution is basic. In part C, they give you a 0.140 molar HI aqueous solution. HI is a strong acid solution. Since it is a strong acid, it will dissociate completely according to this reaction. HI aqueous plus H2O liquid results in H3O plus aqueous plus I negative aqueous. Since there is 1 mole of H3O plus formed for every 1 mole of HI dissociated, the concentration of H3O plus equals 0.140 molar. To find the pH, take the negative log of the H3O plus, which equals the negative log of 0.140. The pH of the solution equals 0.85. To calculate the pOH, plug the pH into the equation pH plus pOH equals 14.00. Then subtract the pH, and you have the equation pOH equals 14.00 minus pH, and you find pOH equals 14.00 minus 0.85, which equals 13.15. The pH of the solution is less than 7, therefore the solution is acidic. For part D, they give a 1.25 times 10 to the negative 3 molar solution of SrOH2 aqueous. SrOH2 is a strong base solution. Since this is a strong base, it will dissociate completely according to this reaction. SrOH2 aqueous results in Sr2 plus aqueous plus 2OH negative aqueous. Since there are 2 moles of OH negative formed for every 1 mole of SrOH2 dissociated, the concentration of OH negative equals 2 times 1.25 times 10 to the negative 3. Therefore, the concentration of OH negative equals 2.50 times 10 to the negative 3. To find the pOH, take the negative log of the OH negative concentration. take the negative log of 2.50 times 10 to the negative 3, and you get 2.60. To calculate the pH, plug the pOH into the equation. pH plus pOH equals 14.00. Then subtract the pOH, and you have the equation pH equals 14.00 minus pOH. pH equals 14.00 minus 2.60, which equals 11.40. The pH of the solution is greater than 7, therefore the solution is basic. For part E, they give you 0.340 grams of LiOH in enough water to make a 500.0 milliliters of solution. And they also give you the molar mass of LiOH as 23.9 grams per mole. First, we need the molar concentration of LiOH, so calculate the number of moles of LiOH. Take the number of grams and divide it by the molar mass. Then we have 0.340 grams divided by 23.9 grams per mole, which equals 0.1423 moles. To find the molar concentration of LiOH, divide by the volume in liters. The volume is given in milliliters. To find the volume in liters, divide 500.0 milliliters by 1,000, and you get 0.50 liters. To find the molar concentration, take the 0.1423 moles and divide it by the 0.500 liters, and we have 0.2846 molar. LiOH is a strong base solution. Since it is a strong base, it will dissociate completely according to this reaction. LiOH aqueous results in Li plus aqueous plus OH negative aqueous. Since there is 1 mole of OH negative formed for every 1 mole of LiOH dissociated, the concentration of OH negative equals 0.2846 molar. To find the pOH, take the negative log of the OH negative concentration. Take the negative log of 0.2846 and you get 0.55. To calculate the pH, plug the pOH into the equation. pH plus pOH equals 14.00. Then subtract the pOH and you have the equation pH equals 14.00 minus pOH. And you have 14.00 minus 0.55, which equals 13.45. The pH of the solution is greater than 7, therefore the solution is basic. 2. Calculate the H3O plus concentration of the following solutions at 25 degrees Celsius. Indicate if they are neutral, acidic, or basic. A. pH equals 7.00. B. pOH equals 8.98. C. pH equals 12.87. D. Concentration of OH negative equals 8.76 times 10 to the negative 6 molar. To calculate the H3O plus concentration from a pH value, you need to do the opposite of the log function, which is to take the 10 to the negative of that number, or take 10 to the negative pH. You will need to express the number as a negative number and take 10 to this number. To find the OH negative concentration from the pOH, take 10 to the negative pOH. For example, for letter A, they give you a pH of 7.00. To find the H3O plus concentration, take the negative of 7.00, which is negative 7.00, and then take 10 to the negative 7.00, which equals 1.00 times 10 to the negative 7 molar. Since the pH equals 7.00, this is a neutral solution. For part B, they give you a pOH of 8.98. First, find the pH value from the equation pH plus pOH equals 14.00. Then subtract the pOH and you have the equation pH equals 14.00 minus pOH. And you have 14.00 minus 8.98, which equals 5.02. To find the H3O plus concentration, take 10 to the negative pH, which equals 10 raised to the negative 5.02, which equals 9.55 times 10 to the negative 6 molar. The pH of the solution is less than 7, therefore the solution is acidic. For part C, they give you a pH of 12.87. To find the H3O plus concentration, take 10 raised to the negative pH, which equals 10 raised to the negative 12.87. Therefore, the H3O plus concentration equals 1.35 times 10 to the negative 13 molar. The pH of this solution is greater than 7, so this is a basic solution. For part D, they give you a concentration of OH negative equals 8.76 times 10 to the negative 6 molar. To find the H3O plus concentration, you could find the pOH, then utilize the equation pH plus pOH equals 14.00, then eventually solve for H3O plus concentration. Or you could use the other equation that relates H3O plus concentration to OH negative concentration, which is the concentration of H3O plus times the concentration of OH negative equals 1.00 times 10 to the negative 14. Solve for the concentration of H3O plus, and we have 1.0 times 10 to the negative 14 divided by the concentration of OH negative. We then have 1.0 times 10 to the negative 14 divided by 8.76 times 10 to the negative 6. The concentration of H3O plus equals 1.14 times 10 to the negative 9 molar. To find if the concentration is acidic, neutral, or basic, we should calculate the pH. Take the negative log of 1.14 times 10 to the negative 9, and the pH equals 8.94. Since the pH is greater than 7, the solution is basic.